Thanks everyone, and thank you Marco also for inviting me today to give a talk about active learning in computer vision. So as you see from the slide, my background is mostly in computer vision, so we transition a bit from NLP and speech recognition to this field. Before jumping right into the active learning field, I want to give a quick overview as well about myself, the background, and also the company. So you see here a bunch of companies we work with, most notably Audi for the driving assistance system. So actually we figured out last year that some data they curated with our platform has made it to a series car. So if you drive a very new Audi, there's a certain chance that you used a little bit of our technology. And with iRobot, we work with the Roomba team. So we're trying to make sure that the vacuum roboter is not going to drive into cat poop or dog poop, trying to make sure that everything is safe at home. So about myself, I have a background in engineering. I worked at the Swiss Stock Exchange in the innovation team, and then went back to uni to focus on machine learning. I was in the lab of Luc van Gool, who is a well-known figure in the computer vision space. And I was very fortunate to have really cool supervisors that allowed me to publish at various conferences as well in the field. And while studying at ETH, it was very theoretical, so I was really bored about that, and I wanted to do a bit more applied stuff. So you see a bunch of projects I was also trying to participate in and kind of escape the everyday life of formulas and math. And one of them being an exoskeleton we built for paraplegics. So it's basically like a Iron Man robosuit for people that cannot move anymore, the lower limbs, to make them walk again. And as you can imagine, that's a very complex system with a lot of different sensors and algorithms running there. And the second one is more related to today's talk. It's ASIC. So an ASIC is an application-specific integrated circuit. It's basically when you take a CPU or GPU and you just make it do only one thing and do it really well. It's basically like a chip in the end. We called it Chipmunk. So what we basically did back then is we built the world's first LSTM accelerator. Now, in 2016 and 15, LSTM was a big thing. It was from Schmidhuber and Hochreiter. It was the long short-term memory networks. Back then, it was state-of-the-art for, I think, running on smartphones, running for speech recognition, translation tasks, and many more things. And I'm a very entrepreneurial person, but I'm really happy that I didn't pursue a startup around this topic, because as you could imagine, it takes like 5-6 years to get from a research project to production, and I would stand around now with a LSTM inference chip that would be state-of-the-art, but everybody is using transformer models. So that wouldn't work very well. And so basically, I started after uni lightly. I co-founded a company, and we're an official spin-off from ETH Zurich. We work with companies in Europe and in the US. And we made it to Y Combinator, which is a well-known startup accelerator that also funded startups like Airbnb and Dropbox. So today I'm going to talk about active learning. And to talk about this topic, I want to start a bit with an overview of how typically pipelines look like in computer vision in a simplified way. On the very left side, you basically see how data is ingested or collected. The data there could be static, could be just a bunch of images in a folder or in a cloud bucket. It could also be more dynamic, which is something we see very often in real industry settings. So there's a constant inflow of new data from different production systems. And what companies then do is they take a little bit of that, they feed it through this pipeline, they squeeze it through. And the first important step there is basically the data labeling part. So you take the data, you feed it to give it basically to humans to annotate it. Humans would do drawing bounding boxes or add some tags to the images. So we have enriched them and we can use them for supervised training. And then finally, we train a model, like an object detector or a classification model that does its duty. And if it's good enough, we can deploy it to a production system. Now, the problem here is that usually the data the companies have on the very left side is significantly more than what they can use. And they need some mechanism to subsample or select what data is actually useful. And now you could imagine all the companies in the industry, they use the latest and greatest papers from NeurIPS or ICML on how to do data selection or active learning. Unfortunately, it's not the case. The most common method used in industry is just random sampling. And it's simply because it works very well, and it doesn't change any statistical distribution of the data you have. So what we do with Lightly is basically we try to bring active learning from academia to industry, help the companies select more useful data for their pipelines. What's important to note here is that most companies only select 1% or less of the data they have. So only 1% is going to be used. And which 1% they pick has a pretty significant impact, as you will see later. And creating this feedback loop from the model training basically back to selection and then going through that as an iterative process, this is commonly known as active learning. We call it like a training loop. And then you can do the same with systems that are already deployed. So you can also kind of create a production loop. So you get feedback from users and you further improve the system. And the goal of this data selection step is basically to pick the next batch of most useful images, or it could also be text in NLP or audio, just the next batch of data for data labeling, and then finally for model training. There are a bunch of challenges with this technology. That's also one of the reasons why it didn't make it very successfully so far in industry. I'm teasing a bit here because I think in the big labs all use it. So Google and all the big ones, they use active learning heavily and rely on it. But I feel like for a lot of smaller teams, it's very difficult to get it working well. And one of the challenges here is basically described. So when you do data sampling, it really matters on whether you have a very, very small amount of data, you're kind of in a scarce domain, or whether you're in an area where you have just plenty of data. If you have plenty of data, like, I don't know, you pick 90% out of 10,000 images or something, that's more in the high data regime. Methods that work there well don't perform well in the low data regime. And one simple example that we have seen plenty of times is methods that rely on diversity of the data. So what you can do is similar to what the other Igor previously described very nicely is you can take the data, feed it through embedding models, and then you can use these vectorized representations to diversify the data set. So you can use methods like corset to find the set that spans the whole space of data, and you kind of remove the nearby duplicates. And this works well. It works actually so well that you not only outperform random, you can even get a better model. So while keeping the validation set the same and only reducing the training set, you can improve your model accuracy. Really kind of just get rid of the garbage. But the same method performs very, very badly in the low data regime. Because if you only pick the diverse examples there, what you end up having with is just the outliers. And if you ever try to train a neural network or machine learning model only on outliers, it's very, very difficult to get that to work very well. So that's one of the challenges a lot of people face in industry, because first of all, they need to figure out in which domain they are, and then they need to change algorithms and have a flexible framework to go back and forth. So what typically is done is people use something like predictions from a model. It could be just a single model, or it could be an ensemble where you do some Bayesian inference. You try to get some information. For example, if you have 3 models, you can do some aggregation. If 2 models think something is a dog and 1 model thinks it's a cat, there's probably more information in this sample than if all 3 models agree it's a dog. So you can use some information like that to figure out what data is actually useful. And we can also use the predictions of the models for balancing across different categories. So if you already know that my model predicts 90% of the data consists of dogs, but we don't have enough cats, we can oversample the more rare class. So we can go much further than that, and a bunch of new papers suggested, hey, we can also use embeddings. We can use embeddings to additionally get signals from the data. So we can not only look at where my model thinks it's struggling, we can also consider how similar is this particular example we're looking at compared to the existing training data, or also compared to other data we have. And we can use the embeddings for diversity sampling. So again, we can try to find more outliers, or we can also use them for similarity search. So if we know that we have a certain example or group of examples where the model doesn't work at all, we can try to mine in a huge pool of unlabeled data for more examples. And at our company, we even went one step further because there's one additional source of very useful information. It's metadata, and it very often comes for free, especially in industrial settings. Whenever you have a camera that takes pictures, you might also have a timestamp. You also have a location where the data is collected and other information. So we can use that to additionally balance across locations. We can use it to also exclude data that doesn't fulfill certain metrics. And what we basically built at Lightly is just a framework that combines all of them together and makes it easy accessible to pick whatever works best. Now, for the metadata, it's rather easy. We have sensor values from the company. They might have some information about the GPS location or the timestamp. And for the predictions, we can use the model they already have, so we can improve the model. The remaining question is how to get good embeddings. And for that, there are 2 free options that are commonly used. The most simple one is you just take a large pre-trained model. It could be something like a ResNet pre-trained on ImageNet. In computer vision, it could also be a Dino V2 model, which is trained on a larger data set. That's one of the options. The other one is that we can take the model the customer tries to improve. So if you have an object detection model that you try to improve, you can basically use one of the last layers there and use that as an embedding vector. The problem there is that whatever model flaws we have in the model then also are in the embedding space. So if your model is mostly focusing on 2 classes, the embedding space would also be clustered mostly in 2 classes. So there's some disadvantage on that. And the third option, it's basically what we do, is you take these very large pre-trained models and you fine-tune them on the data. And to do that on unlabeled data, we use self-supervised learning. And we built our own internal framework and basically open sourced it. And in the meantime, it became the biggest open source framework for self-supervised learning in computer vision. It's under MIT license, so a bunch of companies also use it commercially. I met a ML team from Jabra, actually. They use it now for the video conferencing system. It's pretty exciting. And it's built on top of PyTorch. It's very modular. And we use it actually for all our customers. So Audi, iRobot, all of them are also using self-supervised learning already for a while to train embedding models specifically on their data set. And that works very well, as we will see now. So let's see a real-world example, basically. First of all, we have a toy data set, agriculture data set for object detection, and we take a typical model that is used in that space. It's like a YOLO V8. If you ever try and train the object detection model, you might be familiar with the YOLO series. So it's a single-stage detector, and the goal is basically to detect the bounding boxes of the class of interest and the class category. What you're looking at here is there are a bunch of plots on the left side, and the important thing is that on the x-axis, we look at the training set size, so the total number of images that we use to train a model. We start with 200 images, and then we go on to 400 images in total, and on the y-axis, you see the validation accuracy. So for validating the model, we keep a holdout set, a separate set that we use just for validation. We do not touch it at all. The only variable we have here that we change is which 200 images we add to the initial 200 images. So you see that by all the lines actually starting at the same spot on the 200 x-axis. So all the models start with the same base setup, basically. And if you look at the numbers, I think it's 52.5% mean average position accuracy for the 200 samples. And as you can imagine, adding more data, even randomly, improves the model accuracy. So we go up with I think you can follow the red line there. I think we go up by like 1%. The interesting thing here is now that if you use different active learning methods, some of them improve the model accuracy by a significantly higher margin. Especially if you use all, which is basically just like throwing all the methods in, you get up a much higher gain. I think it's over a factor of 2 higher. And then we can do a different ablation study where we basically deactivate some of these methods. Then on the right side, we look at the same plot, but this time we also look at the fine-tuning of the self-supervised learning model for the embeddings. And as you can see, the fine-tuning additionally increases the accuracy for some of the experiments. So it's kind of a great example to see how things can actually work then in real world. And it's very easy to do these ablations because we parameterized everything. So it's just a config file where you do your experiments. We also have another case study. Basically, we did with a larger customer in the automotive field or in the, let's say, robotics field. One of the common challenges there is basically that when you build an autonomous car, you want to detect where the car can drive, or the robot. We have the same actually with the customers in the delivery space. So they have some very cute tiny robots, and they need to figure out if they can go on the street or not to bump in a tree. And it's a tough challenge because there's a lot of area to map, right? There's a large image, like large resolution camera, and you want to be sure that you do this properly. So in this case here, we're more in the high data regime, not anymore the low data regime. And they actually already did a lot of work. They annotated 10,000 images. And if you've ever done segmentation annotation, you would know that it can take up to 1 hour for a single image, and it can cost you up to $5. So getting 10,000 images annotated is already pretty costly, also in time. And they already had at the time 100,000 unlabeled images available. And the task was basically, hey, out of these new 100,000 images, which 1,000 images should we take? And they did ablations with different methods. So once randomly adding 1,000 more images, and once picking with lightly. And in this case, we focused on diversity, as I showed you in one of the earlier slides. And picking or adding the most diverse 1,000 images to the existing set improved the model accuracy by a significant margin. So in this case here, they also got over 3 times more value added for the same amount of additionally labeled data. That's already all from my end. Thanks a lot for the...
Thank you very much, Igor.